Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. Today we are going to discuss about the module Solar Cell Efficiency and its losses from the paper Energy-related materials. The main points which will be covered in this module are: what is solar cell efficiency? Second, the efficiency losses. Thirdly, we will be discussing about the factors affecting the efficiency of solar cell. Fourth, the technology to reduce the efficiency losses. So students, let us start with a brief introduction about the module. Photovoltaics is the process of converting the sunlight directly into the electricity using solar cells. Today, it is a rapidly growing and increasingly important renewable alternative to the conventional fossil fuel electricity generation. But compared to other electricity generating technologies, it is a relative newcomer, with the first practical photovoltaic devices demonstrated in 1950s. Research and development of photovoltaics received its first major boost from the space industry in 1960s, which required a power supply separate from grid power for satellite applications. These space solar cells were several thousand times more expensive than they are today, and the perceived need for an electricity generation method apart from the grid power was still a decade away. But solar cells became an interesting scientific variation to the rapidly expanding silicon transistor development, with several potentially specialized niche markets. It took the oil crisis in the 1970s to focus the world attention on the desirability of alternate energy sources for terrestrial use, which in turn promoted the investigation of photovoltaics as a means of generating terrestrial power. So, although the oil crisis proved short-lived and the financial incentive to develop the solar cells elevated, solar cells had entered the arena as a power generating technology. Their application and their advantage to the remote power supply areas was quickly recognized and prompted the development of terrestrial photovoltaic industry. Small-scale transportable applications such as calculators and watches were utilized, and remote power applications began to benefit from photovoltaics. In 1980s, research into the silicon solar cells paid off, and solar cells begin to increase their efficiency. In 1985, silicon solar cells achieved a milestone of 20% efficiency. Over the next decade, the photovoltaic industry experienced steady growth rates of between 15% and 20%, largely promoted by the remote power supply market. The year 1997 saw a growth rate of 38%, and today solar cells are recognized not only as the means for providing power and increased quality of life to those who don't have grid access, but they are also a means of significantly diminishing the impact of environmental damage caused by conventional electricity generation in advanced industrial countries. The increasing market for and the profile of photovoltaics that are more application than ever before are photovoltaically powered. These applications ranges from power generation of several megawatts to the ubiquitous solar calculators. The efficiency of a solar cell. Energy conversion efficiency, or eta-S, of a solar cell is a measure of the percentage of power converted from the absorbed light to the electrical energy. The expression for the solar cell efficiency can be written as eta-S is equal to Pm divided by Pn, which is equal to Vm divided by Pn, and this is equal to VOC eta fill factor divided by Pn, where the Vm and the Im are the voltages and the currents at the maximum or the highest power point, which is shown in the figure also. The standard solar radiation, which is known as the AM 1.5 spectrum, has a power density of 1000 watt per meter square. Thus, a solar cell having 1 meter square of surface area and 12% of efficiency will produce 120 watts of power. The maximum conversion efficiency, or the theoretical efficiency, for various semiconducting materials with the energy band gap is shown in this figure. The efficiencies values of these semiconductors were calculated without considering any losses such as reflection, cell resistance, transmission, non-ideal junctions, collection efficiency, etc. It can be observed that the maximum efficiency is a strong function of temperature, and the optimum band gap shifted upwards with increase in temperature. At room temperature, the peak efficiency observed between the band gap ranges from 1.4 to 1.6 electron volt, that is 26 to 29%. The band gap for silicon is 1.1 volt, which is lower than the optimum band gap value and the band gap for gallium arsenide is near the optimum value, that is 1.4 electron volt. Still, the silicon cell efficiency is quite high. Efficiency losses. Now students, let us discuss the mechanism behind the losses of efficiency. A typical PN junction solar cell with the physical arrangement of the major components is schematically shown in the figure. The PN junction produces an inherent electrical field separating the charges created due to the absorption of sunlight. These PN junctions are created by putting a p-type material in a diffusion furnace containing the gaseous n-type dopant. Hence, the n-type dopants gets diffused into the surface up to a depth of about 0.2 microns. Therefore, these junctions are created near the surface where the electrons and the holes created due to the absorption of sunlight moves towards the front and the back of the cell. The back of the solar cell is completely covered by metallic contact, which also collected the total charge from the back side of the cell. A fine metallic grid is used on the front side of the cell that collects the charge from the front side. This collection of the current grid occupied area of about 5% of the total area to allow more sunlight to be incident on the active cell area. Thus, the solar cells do not work at their theoretical maximum efficiency due to various limitations. Some of the limitations can be solved independently, while the others are interrelated. The factors which limit the efficiency of the photovoltaic device are reflection losses, shade due to current collection grid, incomplete absorption of photon energy, excess photon energy loss, short circuit current losses, voltage factor loss, curve factor loss, series and shunt resistance losses. We will be discussing all these factors one by one. Reflection loss. The reflection losses, or the reflection of the incident sunlight from a bare and clean semiconductor materials surface, are very large, which can be reduced by using anti-reflective coating and texturing the semiconductor material's surface. Now let us consider three top layers of PN junction solar cell as shown in the figure, that is a film of a semiconductor material of refractive index N2 and anti-reflection coating or the film of refractive index N1 and thickness D1, and finally a sheet of glass or air of refractive index N0, and the refractive indexes are in the range of N0 is less than N1 is less than N2. Then the expression for the reflection factor or the reflectance is given by R is equal to R1 square plus R2 square plus twice of R1 R2 cos 2 theta divided by 1 plus r1 square r2 square plus 2 r1 r2 cos theta, where theta is the angle of incidence and r1 and r2 are the reflected intensities at the first interface and second interface respectively, and they are given by r1 is equal to n0 minus n1 divided by n0 plus n1, and r2 is n1 minus n2 divided by n1 plus n2. The reflectance R would be minimum at n1 d1 equal to lambda naught by 4, where lambda naught is the wavelength at which the layer is a quarter wavelength in optical thickness. Hence, the minimum reflectance R minimum is given by R minimum is equal to n1 square minus n0 n2 divided by n1 square plus n0 n2, this whole square. The above expression describes that the reflectance will be 0 when n1 is equal to root of n0 n2 at d1 is equal to lambda naught by 4 n1. Hence, there will be only one wavelength for which the above situation will be satisfied, while in practice the reflectance needs to be decreased for a broad band of wavelengths. Reflection loss. This graph shows the special reflectance from the bare silicon coated with the anti-reflective coating in air and the silicon coated with anti-reflective coating with glass at the top. In this figure, the anti-reflection coating of refractive index of 2.3 gives a minimum reflectance at a wavelength of 0.6 micron, which is shown by this dashed pink graph, and it kept under the n0 equal to 1.5. The value of its refractive index increases to 2.3. Several materials have been tried as the anti-reflective coatings on the solar cells, such as magnesium fluoride having refractive index in the range of 1.3 to 1.4, SiO having refractive index in the range of 1.8 to 1.9, SiO2 having N1 is equal to 1.4 to 1.5, Al2O3, titanium oxide, zinc sulfide, Si3O4, and etc. The reflectance can be further reduced by using multiple layer coating. Another procedure that can help in reducing the reflection is to use the textured surface on the face of the cell material through a selective material. The chemical etching of the semiconductor surface gives an appearance of pyramids on the cell's surface, where the light reflected from the face of the pyramids is directed towards the cell, and therefore the light has at least two chances of being coupled into the cell. Shade due to current collection grid. A metal bar grid which is always kept on the top of the solar cell to collect the charge carriers to flow the current in the circuit. The metal grid of suitable design is a must. However, it adds three major problems, such as it increases the series resistance in the form of grid metal resistance. Second, it gives a surface contact resistance between the metal grid and semiconductor material. And third, it reduces the light transmission reaching the semiconductor. During the designing of metal grid, it requires to be made sufficiently thick so that it can provide low resistance and good contact with the semiconductor, giving good ohmic contact. Furthermore, the width of the grid should be very small compared to the front area of the cell, giving little shades. The grid line width and their interspacing can be controlled via deposition or fabrication techniques. Grid line widths up to 20 micron is possible using evaporation through photolithographic technique, and up to 50 microns using screen printing techniques. Incomplete absorption of photon energy. It can be seen from the solar irradiance curve, which is shown on the right hand side, that there is significant portion of the spectrum which has energy of photon smaller than, and the band gap of semiconductor material, that is h nu, is less than Eg, and thus this portion will not generate the electron hole pairs and will not be absorbed in the semiconductor. Let us take an example of a silicon that has the energy gap of 1.1 electron volt. The inactive wavelength corresponding to this gap is lambda is greater than or equal to 1.1 micron, and this constitutes about 23% of the AM1 in isolation. If this amount of energy gets absorbed by these semiconductor, then it will heat the semiconductor material, which unnecessarily increases the temperature and will result in low efficiency. Hence, these photons can either be removed via using special kinds of filters. Excess photon energy loss. The minimum energy of the photon, which is required for generating an electron hole pair, must be equal to the energy gap. However, there are large number of available photons whose energies are larger than the energy gap. These photons with excess energy will cause lattice vibrations, resulting in heating the semiconductor. The calculation of the number of photons in the solar spectrum which have energy more than Eg with different energy gap values like 2.25 electron volt, 1.45 electron volt, 1.07 electron volt, 0.68 electron volt, and 0.34 electron volt are shown in the figure. Now let us discuss about the short circuit current losses. Short circuit current loss is a combination of optical losses comes from three different areas of the cell. First, as discussed earlier, that bare silicon is quite reflective in nature. Hence, the anti-reflective coating of suitable material is required to reduce the optical loss. Second, the electrical contact made with P side and N side of a solar cell results in a metal grid contact at the surface, which is exposed to the sunlight. This blocks 5 to 15% of sunlight. And third, if the fabricated cell is quite thin, then some of the light having suitable energy will pass straight back out the cell. This determines minimum thickness of the semiconductor material required. Hence, direct band gap material will require less material than the indirect band gap material. Another factor which takes part in short circuit current loss is the recombination in the bulk semiconductor and at the surfaces, that is, charge carrier created away from the junction have high probability of recombining before they get separated. Another reason for the efficiency loss which we are going to study is the voltage factor loss. The fundamental process which determines the open circuit voltage VOC is the recombination in semiconductors. Hence, lower the recombination rate of charge carriers in the semiconductor, the higher is VOC. Both the bulk and the surface recombination are important. However, recombination through traps in the transition region can limit the VOC. The expression for recombination through traps within the transition region can be written as USHR is equal to Np minus Ni square divided by tau p multiplied by N plus N1 plus tau n multiplied by P plus P1. This recombination rate will have its peak value when N1, P1 are small and N and P are also small. This happened for the traps near the mid gap within the transition region. In the earlier discussion about the dark characteristics of PN junction diodes, recombination within the transition region was neglected because the depletion region width was very small. However, due to more numbers of recombination, an additional will be introduced in the dark current voltage characteristics as follows, that is I is equal to Is multiplied by exponential QV by KT minus 1 plus IW multiplied by exponential QV by KT minus 1. The second term of above equation at low current, hence at higher current, the above expression can be written as, here we have neglected the second term, that is I will be equal to Is prime multiplied by exponential QV by NKT minus 1, where N is called as the identical factor and it changes with the current level as of Is prime. Its decrease from 2 to 1 at low current to higher current. Hence, the presence of this additional depletion region, the recombination current, can act to decrease the VOC. Curve factor loss. The maximum output power which can be obtained at the point where the largest rectangle can be carved into the current versus voltage characteristic curve. These points are given by Vm and Im on the curve. So the ratio of Vm-Im to VOC-IOC is known as the fill factor or eta FF, and it depends on the VOC, RS and RSH, and slightly on the recombination within the transition region. So this eta FF is equal to Vm by VOC multiplied by 1 minus the ratio of exponential QVM by NKT minus 1 divided by exponential VOC by NKT minus 1. So during deriving the above equations for eta FF, it has been assumed that there is no series or the shunt resistance effect. Hence, in this situation, the expression for eta FF can be broken into two parts as follows. That is, E fill factor eta FF is equal to the curve factor multiplied by anti-facts factor. Curve factor is a function of energy band gap and it increases with the increase in the energy gap. Series and shunt resistance loss. The solar cells generally have parasitic series and shunt resistance associated with them. The current which is produced in a solar cell passes through the bulk before it reaches to the contact grid. In a solar cell, the back side of the cell is fully covered by metallic grid, which reduces the series resistance up to 0. However, the front cover, which is exposed to the light, should be covered by the grid to the least possible value. This will result in considerable long current path lengths and introduces large series resistance. The series resistance Rs arises due to the bulk resistance from the semiconductor, metallic contacts and interconnections and the contact. On the other hand, the shunt resistance, that is RSH, caused due to the crystal defect due to leakage across the PN junction and unwanted foreign impurities in the junction region. Both type of resistances affects the fill factor. Furthermore, very low value of RSH and a very high value of RS can also reduce the VOC and ISC. The effect of series resistance on the fill factor is given by eta fill factor is equal to eta FF naught multiplied by 1 minus RS, where eta FF naught is the ideal fill factor in the absence of series resistance, and small rs is the normalized resistance, which is given by capital Rs divided by RCH, which is nothing but the characteristic resistance. And this RCH is equal to VOC by ISC. Similarly, the effect of shunt resistance on the eta fill factor is given by eta FF is equal to eta FF naught multiplied by 1 minus VOC plus 0.7 divided by VOC, this whole multiplied by eta FF naught divided by RSH, where eta FF naught is the ideal fill factor in the absence of the shunt resistance RSH, and the small RSH is the normalized shunt resistance, which is given by capital RSH divided by RCH. And as you can see that here small VOC is the normalized voltage, which is different from capital VOC, and it is given by capital VOC by NKT by Q. Loss of efficiency of silicon and cadmium sulfide, copper sulfide solar cells. This table summarizes the various losses for the solar cell based on the actual silicon solar cell and cadmium sulfide, copper sulfide semiconductor materials. These energy loss calculations in the solar cell, they were made by Rothwaf, Bohr and Wolf. As discussed, that the band gap of a semiconductor should match the solar spectrum, and the optimum band gap is in the range of 1.1 to 1.4 electron volts for getting high efficiency with high open circuit voltage and high photocurrent from the solar cell. Furthermore, the absorbance of the solar cell should be such a way that it should be able to absorb the entire photons incident on the cell surface. This could be possible only if we use a series of solar cells with varying band gaps and they are arranged in a multi-layer or tandem structure. On the other hand, it can also be achieved by utilizing filters splitting the solar spectrum into different spectral regions and directing the spectral beam of desired spectral range towards the individual cells which have spectral response, and the band gap is suitable to that spectral range. So students, let us summarize what we have learned in this module. The upper limit to the solar cell efficiency lies within 26% to 29% and occurs for the band gap in the range of 1.4 electron volt to 1.6 electron volt. There are several factors combined to ensure that actual solar cell, they have efficiency of somewhat below the ideal one. The solar cell efficiency, it decreases with increasing temperature, primarily due to the temperature sensitivity of the open circuit voltage. Thank you.